Good afternoon, everybody, and welcome back to the RIC. This session is on space nuclear power systems to Cislunar and beyond. And I know I've been really looking forward to chairing this session. It's going to be a lot of fun. When we first started looking at space systems, I know when I came to the NRC in 2018, Mars 2020 was coming into being, and I know that we were starting to develop the National Security Presidential Memorandum 20, and we were going to have a session in the last RIC that really kind of focused on the regulatory aspects and the policy aspects of space nuclear power systems, both commercial and government flights. But since we're a little farther along than that, and we've had a successful Mars 2020, and if you look close on Perseverance, you can see the RTG that's on Perseverance when they show photos, and I know DARPA is doing some really cool stuff, and we've got Nathan Greiner that's going to be able to talk about that, and NASA's got some cool missions going as well. So I thought this year, since things are farther along, we'd talk more about the missions and how nuclear safety plays into the missions. You think, well, what does that have to do with maybe with NRC missions or oversight? Well, the NRC does belong to the Interagency Nuclear Safety Review Board that does do reviews for nuclear space systems, and I'm a member of that board, and Tina Ghosh is an alternate. We've had people work on safety reviews of space missions in the past, but what's particularly interesting, I think, that's going on now with new space missions and propulsion systems, and I know everyone's going to talk about that on the panel, that some of these technologies, I think, will get directly related back to what may turn into commercial applications and licensing of activities and facilities that the NRC does have regulatory authority over. So with that, this is going to be a fun session, and I'm going to introduce our panelists before we get started. The first panelist is Tracy Bishop. She's the Deputy Assistant Secretary for Nuclear Infrastructure Programs at the Department of Energy's Office of Nuclear Energy, and I've known Tracy I've lost count of the number of years, Tracy, but it's been a long, long time, and it's really great working. It was great working with you when I was in DOE, and I'm glad you agreed to participate in this. And Tracy's responsible for the management of the Office of Nuclear Energy's infrastructure programs at the Idaho National Lab and the NE field operations at the Oak Ridge office, and that supports the lease administration of the uranium enrichment capabilities at Portsmouth Gaseous Diffusion Plant. She's the nuclear energy's primary interface with NASA to develop and deploy nuclear power systems to support space exploration goals. And that's what you'll hear from her today. She holds a bachelor's degree in nuclear engineering from Georgia Tech, an MBA from the University of Maryland. She's a certified project management professional, and she received a Presidential Rank Award in 2015 for her accomplishments in the area of nuclear infrastructure management. After Tracy, the next speaker is Major Nathan Greiner, and he's the program manager for the Tactical Technology Office with the Defense Advanced Reactor Projects Agency. And we won't be able to have Nathan on video, but he will. We'll show his picture and his slides, and he's there by voice. So Nathan's with us. Major Greiner, I joined DARPA in 2018 as a program manager in the Tactical Technology Office. His interests include advanced power and propulsion technologies for land, sea, air, and space applications. And before joining DARPA, Major Greiner completed a one-year fellowship at the Oak Ridge National Lab in Oak Ridge, Tennessee, where he focused on material research. And he has had a whole bunch of Air Force assignments over his career as well, which I won't go over many of them. Nathan, I don't know how you've done all of this stuff in your career. It's quite amazing. But Major Greiner, he holds a PhD in aeronautical engineering from the Air Force Institute of Technology, a master's in science and mechanical engineering from the University of Utah, and a Bachelor of Science in Mechanical Engineering from the University of St. Thomas in St. Paul, Minnesota. He currently manages the Glide Breaker Hypersonic Defense Demonstration Rocket for Agile Cislunar Operations, better known as DRACO to us, nuclear thermal propulsion, and advanced full-range engine programs at DARPA. So thank you for joining us, Nathan. And our other panelist is Dr. Anthony Calomino. He is the Space Technology Mission Directorate Portfolio Manager in NASA. And he manages the space, nuclear, and power propulsion technologies under that NASA directorate. And he has engineering degrees in structural analysis, engineering mechanics, and materials science. Dr. Calomino's expertise is in durability analysis and damage modeling of high-temperature materials and composites, extending from metallic superalloys to ceramic matrix metallics, or composites, ablators and refractory soft goods. He has worked in nuclear fission technology development for NASA since 2016. So with those introductions, I'll turn it over to you, Tracy, for your presentation. And if we could have Tracy come on the screen along with her slides, that'd be great. Tracy?
Thank you, Ray. Thank you for the introduction. It's great to be here today to talk about what the Department of Energy is doing for the space effort in totality. Next slide, please. So as you can may or may not know, the Department of Energy has spent over the last 60 years being a key part of space nuclear power and propulsion for the U.S. government, going back to the beginning of the space race in the late 1950s, where they first started developing radioisotope power systems, particularly radioisotope thermoelectric generators under the Atomic Energy Commission, and moving on to bigger and better efforts, including supporting weather satellites, involvement with the Apollo missions to support experimental activities, also designing and deploying a reactor in the mid-60s to test the capability in space. And then moving on into the 70s and the 80s into more deep space missions and powering probes, including some big ones like Pioneer, Voyager, New Horizons, Ulysses, and as Ray mentioned, moving into rover capabilities, including the Mars Science Laboratory, and the latest Mars 2020 Perseverance rover, where you can see the MMRTG very clearly on the top of the rover, which is powering not only the rover, but the helicopter as well as part of the whole experiment package. Next slide, please. So the Department of Energy is probably not thought of as having a role in nuclear space power, but we do serve as a technical design authority for space nuclear power propulsion systems that have been designed through our agency and its predecessors. And those two areas are focused on radioisotope power systems and nuclear fission power systems as well. How do we do this? We enable the work through our National Laboratory Complex, research and development areas in a wide range of technical capabilities to advance these technologies. As you can see, it's DOE in partnership with the National Nuclear Security Administration. We have a number of national laboratories. The few I have highlighted here are key laboratories that are involved with space activities. They are part of a consortium led by Idaho National Laboratory, Los Alamos National Laboratory, Oak Ridge, and Sandia National Laboratories. The other thing that the department has through our unique role with its authorities through the Atomic Energy Act is we can extend nuclear safety and business frameworks to other federal agencies in order to provide a basis to be able to execute nuclear missions and also provide the safety oversight and analysis work. Next slide, please. So briefly, what is our two main technology areas? The first one is radioisotope power systems. Those systems enable and enhance missions by providing electrical power to explore environments where solar power and other chemical batteries is not feasible. And that's through spacecraft operation and things like instrumentation. Basically, it converts heat from radioisotope into electricity through the use of thermocouples. The heat is a product of natural isotope decay, and we utilize plutonium-238 in a ceramic matrix. It's the isotope of choice due to its long half-life and high energy alpha particle. And I have a few diagrams and pictures here on the side. And in the far bottom right is a picture of a P238 fuel pellet, which is uncladded. And yes, that is the actual color. It does glow very hot from that decay product. And then we also have some schematics here. There is a radioisotope heater unit, which is a very small design, which is a very small 2-gram pellet that can be put in with instrumentation to keep them warm. And then we utilize the fuel clads and put them into general purpose heat sources, and that's the battery that powers our radioisotope power systems. Next slide, please. As I mentioned before, we've had a number of power systems that have evolved over the decades. Some I've highlighted here, just a few of the major ones. First one was SNAP 27, which was approximately 70 watts electric. That was primarily utilized for the Apollo missions. The astronauts actually carried these and put them in place and to be able to perform some of the first series of experiments for NASA in order to gain and learn additional information and data. As we moved on and started deploying the deep space probes, we moved into the SNAP 19 designs, which are about 40 to 45 watts electric that were utilized for the Viking and Pioneer missions, and then moving into the multi-100 watt systems into the late 70s with the Voyager 1 and 2, and then eventually into the general purpose heat source RTG, which was approximately 300 watts electric that was utilized in the 80s and the 90s. And that was something through the 2000s with some of the big missions with Galileo, Cassini, and New Horizons. Next slide, please. So currently we have 3 systems that are flight certified. The first one is the multi-mission radioisotope thermoelectric generator, which is pictured on the top right of the screen. That is a system that was utilized for both the Mars Science Laboratory as well as the Mars 2020 rovers. It produces roughly 110 watts electric each. The next system we have that's still flight certified, although the last time we used it was New Horizons, is the GPHS RTG. The final system we have is the radioisotope heater units, and those are small pellets to keep instrumentation warm. But we're continuing to work and move forward with NASA, looking to the future as far as what is the next step in the next evolution of technology. So right now we're currently working on 2 technology development areas. The first one is the next generation radioisotope thermoelectric generator, which is focused on essentially being the next modification to the GPHS unit. NASA has identified a need to have larger power systems. So we're in the process now of working with them in industry to look at those designs and look at options to be able to revamp that technology going forward. And the second area is a dynamic radioisotope power system, and that's utilizing either a different power conversion system, but that's not passive, it's thermocouples. It would be utilizing either Stirling or Brayton cycle to be able to improve efficiency of the RPS unit. Next slide, please. So how does the department execute on the radioisotope power system production? Well, it's a multi-laboratory effort that takes a few years to go through the entire process, which starts at the very beginning, which is plutonium isotope production. Since 2015, we've reestablished the capability to produce domestic isotope activities, and that starts with Oak Ridge National Laboratory, where they fabricate Neptunium-237 targets for radiation. Those targets are then irradiated and put into a high-flux isotope reactor in Oak Ridge, or the Advanced Test Reactor at Idaho National Laboratory, where they go in for irradiation cycles. Once the targets are irradiated, they go back to Oak Ridge National Laboratory, where the 238 is separated and put into an oxide form, and then shipped to Los Alamos National Laboratory, where at Los Alamos National Laboratory, the heat source oxide is pressed and put into pellets and encapsulated, utilizing some of the fuel that's present at the lab, and also utilizing cladding that was produced at Oak Ridge National Laboratory. Once the pellets are assembled and encapsulated, the heat source assembly process then moves to Idaho National Laboratory, where the INL, they take the encapsulated fuel clads, they put them into a general purpose heat source, and then build and assemble that heat source into the generator, test it, verify it for flight, consistent with NASA requirements, and then provide support to ship the system off to Kennedy Space Center, where they work with the mission partners in order to integrate the power system with the scientific equipment, and then support any launch activities, including nuclear safety support and radiological contingency planning. Next slide, please. So in order to, one of the improvements we've done over the last few years is we've shifted our partnership with NASA to focus on having a constant rate production approach to supplying plutonium-238 isotopes and heat sources to support NASA's missions. Previously, this work had all been done on a campaign mode, where a mission would come in, we would retrain people, bring the equipment back up to operational status, manufacture the fuel, and then put everything back in cold standby. Well, that's a very expensive and time-consuming process in order to operate nuclear facilities in that manner. And it also put a lot of risk onto the missions. So a few years ago, we shifted to having a stable production rate that was based on NASA mission requirements, with the goal of producing 1.5 kilograms per year of heat source plutonium oxide by the mid-2020s, as well as being able to produce and manufacture 10 to 15 fuel clads per year. This was felt to be a good throughput that would continue to exercise the equipment, make sure that we had a continuous production rate going forward with material, and actually have material on the shelf to support future missions. And that really was a very effective and cost savings measure, because we're projecting that the actual cost to the missions would be reduced by roughly 25%, and also take about 2 years of schedule risk off of a future RPS mission. So it's just something that we're trying to work on to ensure that we've got this viable capability going forward, and it can meet growing mission demands. Next slide, please. So the second technology we focus on are nuclear fission power systems, and these are systems that utilize fission reactions to generate power for space applications. This is an area where we've had lots of starts and stops over the decades. As I mentioned earlier, we successfully launched the SNAP-10A back in the 1960s, which is a U.S. Space reactor. Now, we've also had nuclear propulsion research and demonstration programs that were established in the 1960s. NRCgov and the Kiwi activities were some of the examples of those. And since those major programs terminated in the early 70s, there's been modest efforts since then to continue to evaluate and move designs forward. The SP100, that's an example I have down there, but there's been others throughout the efforts. You'll hear some more about those from my other panel members here in a little bit. One of the benefits that we're seeing now, and there's been such a growth in this area, is there's a lot of natural synergy with the DOE missions that support the commercial nuclear power industry, especially with the new microreactors and small modular reactor efforts. Areas such as fuel qualification and development, design and demonstration of these small reactors, and then also modeling and simulation capabilities. So this is just such a great time right now, so that where we've got a lot of different entities who are interested in the same things to be able to partner together and continue to move the technology forward. Next slide, please. And just as I don't want to elaborate in this too much, but currently we're supporting fission surface power demonstration activities to look at for sustainable power source for nuclear demonstration by 2028 in the 10 to 40 kilowatt electric range. We're also working on nuclear thermal propulsion, where we're looking at establishing technical foundations and also supporting experimental programs, particularly with the treat reactor, where we're doing a lot of fuel testing and development. Other things we're working on too is there's a common field development program for both terrestrial and space use, looking at coated particle fuel, for example, to see where we can gain synergies and also be able to leverage common platforms, common manufacturing applications. Next slide. So what does DOE bring to the table here? Well, DOE and through our national labs just has extensive capabilities for fuels and materials research and development, qualification for technologies, and being able to demonstrate performance and safety of systems. Over the last decade or so, DOE has really stepped up and invested heavily in capabilities to support the commercial industry, from irradiation, post-irradiation examination, looking at different fuels, modeling simulations, and even moving into demonstrations. And we continue to look for opportunities to leverage these existing facilities and capabilities and technical collaborations between the agencies, industry, and universities to work and drive the technology to the next levels. And the pictures here on the slide are just pictures of our three our reactors. We've got the advanced test reactor, the high-flux isotope reactor, and then the treat reactor. All three of those play just key roles in all of these areas. Next slide. Nuclear safety framework. This is something Ray just mentioned. So we also, one of the benefits the department has is we leverage our nuclear safety framework to support all of the space nuclear power and propulsion technology activities. The new space policy, such as the National Security Presidential Memorandum 20, really aligns to the DOE nuclear safety model and provides transparency for safety reviews. This was such a key game changer. It established risk-informed approval levels for nuclear launches. Prior to that, all nuclear launches, regardless of how much material was on there, all went up to the presidential level for approval. So this really aligned and put the risk commensurate, and the approvals commensurate with the risk at threshold levels. It also established very clear nuclear safety guidelines for government launches. And it also reduced the regulatory burden and supports really future commercialization goals by setting expectations that are already rooted in our existing U.S. commercial nuclear industry policies and regulations. So it focuses on looking at risk in terms of maximum exposed individual. It sets thresholds that are consistent with both the DOE and the NRC regulatory framework. So it provides a lot of expectation setting up front. And I think that's one of the things where when they looked at the prior process, there was a lot of questions because it was a very long process. It took about 7 years to get through that. And it was identified as one of the higher risk issues with trying to get to a launch approval of the end state. And as you can see here on the picture, this is a picture of the Mars launch back in July. Next slide, please. Also wanted to mention too the DOE-NASA partnership model. So over the last few years, we've really strengthened our partnership with NASA, and we put this structured framework in place to leverage our DOE's self-regulation authorities and indemnification abilities along with our contractual and business process. And the way we do that is we have a interagency memorandum of understanding with NASA that was signed in October of 2016, and that sets the high-level agency roles and responsibilities. It also provides indemnification protection for NASA and its contractors. And that is the governing document. And from that document, we developed interagency agreements. And here you'll see two. One is focused on the radioisotope power systems, and the second one is focused on nuclear fission programs. From there, we set, those are 5-year agreements that set very broad funding authorities as well as goals for each of the agencies. From there, we establish 1-year project plans, and that goes to the next tier down. And as you can see for the radioisotope power system, we have our constant rate production activities. We also have new technology, and then we'll also have individual missions, and I'm showing right there the Dragonfly mission. For the fission, we have both nuclear thermal propulsion and we have surface fission power as well. In the strategic, from there, we develop detailed strategic partnership plans. Those are really our contractual agreements with our national laboratories so that NASA can utilize our national laboratory expertise and be able to assign work authorities to them to accomplish the work. And this has worked very well. It also gives a lot of transparency, and it allows NASA and other agencies too to be able to leverage DOE and its contractors to be able to go out and partner with industry, universities, and other entities to be able to further the mission goals. Next slide. In its summary, I hope as a takeaway today that you recognize that DOE is really a key partner that we work to help enable our mission launching agencies. And we really work hard to improve and continue to strengthen those interagency and industry collaborations and be able to provide a forum to help progress the development of this technology to support the overall U.S. space goals. And with that, I am done with my presentation. Thank you, Ray.
All right. Thank you very much, Tracy. And I appreciate the little history lesson and also what's been going on recently in the Department of Energy as well. And we do have several questions coming in, but we're going to save them until after all the speakers have had a chance to discuss their programs, since some of the questions may get answered in those other presentations. So with that, I'd like to bring in Major Nathan Greiner from DARPA, and he's going to talk about which is a really cool project called Draco, and he's going to explain what DARPA is doing in the area of space nuclear propulsion. So, Nathan.
Thanks, Ray, and thanks for the introduction. This is a really exciting opportunity for us to share about a very exciting project that we're taking on here at DARPA. As Ray introduced, we call this program the demonstration rocket for agile cislunar operations. So I've been gifted to be the program manager for this project that we've kind of been working to get underway for about the last 2 years here at DARPA. Go ahead to the next slide. So a little bit of an overview of what it is that we're trying to do with Draco, right? So with Draco, we're really trying to develop leap-ahead propulsion technology for space applications, right? And really, when you look at this kind of slide in the bottom, the square in the bottom left there, we really have two kinds of propulsion on orbit right now. We have electric propulsion, which has very high efficiency, very high specific impulse, but very low thrust, right? But then you have another, which is chemical, which is in the bottom right of that part, which has very high thrust to weight, but has relatively low efficiency, relatively low specific impulse. And so what we're trying to do with this project is to develop nuclear thermal propulsion. And for those not as familiar, right? So the slide on the square in the bottom right there. With nuclear thermal propulsion, what we do is we take the lowest molecular weight propellant that we can find, right? Which is hydrogen. We bring in liquid hydrogen into our propulsion system, as depicted on the left side of that graphic. It goes through a turbo pump in order to actually raise the pressure of that propellant, and then we flow that propellant through a reactor, split atoms, big atoms into small atoms to release heat, deposit that heat into the propellant, and heat that propellant from cryogenic temperatures on the order of about 20 Kelvin up to extremely hot temperatures up to 3,000 Kelvin, and then push that now extremely hot gas through a nozzle and expand it in order to actually be able to produce thrust. And what that does is allows us to produce a propulsion system that has thrust to weights that are very similar to chemical propulsion systems, but has much higher efficiencies, right? Much higher specific impulse, up to about 2 to 5 times higher. And that really allows us to do some new missions on orbit in order to get this kind of leap ahead of propulsion. So specifically on Draco, we are interested in actually developing a high-assay, low-enriched uranium nuclear thermal propulsion system, and then launching it to above GEO, putting on orbit above GEO, and demonstrating that system in about the 2025 time frame. And one of the reasons that we're looking to actually demonstrate this on orbit is because we really don't have the facilities on the ground in our modern era to be able to actually demonstrate this system at full power on the ground, right? So what that leads us to is that if we want to get a first demonstration complete without building new facilities here on the ground, then we're really forced to go up and do an on-orbit demonstration. So that really is the overall objective of the Draco program. Go ahead to the next slide. So Tracy talked about this a little bit already, but we've been launching radioisotope thermoelectric generators for decades. Almost 6 decades. We've been launching these systems, and so launching of RTGs has become somewhat of a commonplace, among missions that are going, to Mars and beyond. But launching a reactor into space has an entirely different safety profile compared to radioisotope thermoelectric generators, RTGs. So one of the first RTGs that we had launched was the SNAP-3B RTG back in 1961, and as Tracy had said, these systems use plutonium-238, which decays with a half-life of 87.7 years, and so at the time that you launch these systems, they are, quote, on, right? They are producing heat, they are actively decaying as radioisotopes, and modern multi-mission RTGs typically launch with around 60,000 curies of radioactivity at launch, and so that's not an insignificant quantity. And obviously, we've found ways to work with this, and a lot of the safety measures that we apply to RTGs, as Tracy mentioned, are really about containing the system, right? It's about encapsulating the system so that if there is an accident on a launch, that we're able to contain the radioisotopes such that we don't disperse radioisotopes, to places that we don't want them, right? So they really focus on kind of containing that radioisotope. Now with Draco, this will actually be the first launch by the United States, I should say, of a nuclear reactor since the SNAP-10A reactor was launched in 1965. And again, we're doing that because we don't have, the suitable ground facilities for demonstrating the system on the ground. Now, in comparison to an RTG, a reactor at launch only has about 2 to 3 curies of radioactivity from some of the radioisotopes, isotopes of uranium that are in the reactor. So we really have a very low level of radioactivity in the reactor actually at launch, especially compared to RTGs. But again, there's just an entirely different safety profile around reactors because with the reactor, when we launch it, the reactor has at that point never been operated at full power, and so it's never been allowed to actually produce or to accumulate an appreciable quantity or inventory of fission products. And so, when we launch them, when we launch a nuclear reactor, our focus from a safety perspective is really around how do we prevent inadvertent criticality on this system. So if the reactor, if the system were to be launched and something were to happen on launch and the system were to land in the ocean or in wet sand, how do we handle those kind of scenarios so that regardless of what happens to the reactor in an accident scenario, whether it lands in water or in sand or anywhere else, that we don't actually get an inadvertent criticality event. So that really is our focus with regard to launch safety activities. Now, once the system actually gets above LEO on orbit after launch and is safely lofted onto orbit, we're very careful to make sure that the system actually gets launched and placed into what we call a nuclear safety orbit, a nuclear safe orbit, such that if this reactor were to re-enter after orbital decay, that the system would have been on orbit long enough for hundreds of years, such that any fission products from that accumulate after operation of the reactor are allowed sufficient time to actually decay, such that if the system were to re-enter, that it would be at about the same level as when it actually launched, right? At about that same 2 to 3 single-digit curies kind of level. And so really, ultimately what this does, right, is it prevents that even the possibility of having the reactor re-enter what we call a hot re-entry, right, with being able to re-enter with appreciable fission products. And ultimately, this approach meets the guidance that's laid out in the Space Policy Directive 6, which was published on the 16th of December last year. Go ahead, next slide. Okay, so I wanted to talk in a little bit more detail about NSPM 20. Since we're focused, very specifically on this one mission, I did want to talk about NSPM 20 and kind of how DRACO relates to NSPM 20. I really liked what Tracy said earlier, right, about NSPM 20 really being a game changer, right? Because it really is, right, in that it has set an objective regulatory framework, and it kind of has set out this 3-tiered system for how we classify launches that allows us to really tailor how we're going about and approaching our launch approval process in order to help us be able to move fast, get something done, and all the while still be able to objectively maintain the safety of the public. So with NSPM 20, this 3-tiered system, conventional radioisotopes can fall anywhere in this 3-tiered system, really pending what the quantity of the radioisotope is in the RTG and what the overall risk to the public is. Now, with reactors, they per NSPM 20 fall within two tiers, the tier 2 and and Tier 3, each depending on their risk to the public. And what's great about NSPM 20, so NSPM 20 charges us, the sponsoring agency, which in this case, of course, is DoD, with the actual production of a safety analysis report, right? So this allows us to view the objective criteria that are for risk to the public that are laid out in NSPM 20, to design our reactor and design our spacecraft around meeting those objectives, and be able to produce a safety analysis report that shows that we do, in fact, unequivocally meet those objective safety criteria. And then what it does, right, is that we then are able to work directly with the folks in the Interagency Nuclear Safety Review Board, the INSERB, to actually have that board review our safety analysis report, our STAR, and actually document their findings in a safety evaluation report that provides a recommendation on launch safety to the approval authority. And so with Draco, we're 100% absolutely committed to meeting or exceeding the objective safety requirements in NSPM 20. We have been actively engaged with the INSERB folks from the very instantiation of NSPM 20, and we've been working very close, right? Because as Tracy mentioned as well, the former process to be able to go through the safety approval process was a multi-year, high single digits. I think Tracy said 7 years in one example to go through this launch approval process. And obviously for Draco, we're the first reactor. We're the first reactor that's going to be going through this new approval process that was laid out in NSPM 20. And so we're really treading new ground here, which is both exciting and it's also somewhat nerve-wracking, right? In that we want to get from A to B. We want to draw a straight line, but there's always new things that you learn as you go through a new process. And so we're working with the INSERB early and often to make sure that we are on the same page with our path to go forward and meet the guidelines within NSPM 20. We're also working very closely with DOE and DOE labs, specifically with the Los Alamos National Labs and Sandia, to work on our design criteria and our analysis approach to actually meet the NSPM 20. And it's fantastic to be able to work with the DOE folks. They have such a wealth of knowledge working with reactors in the past, and they really have the expertise that we have been certainly relying on and will continue to rely upon for Draco going forward. So it's been great to work with them. And finally, so we're within this three-tiered system for the Draco program. We're seeking to launch under a tier 2 authorization, specifically because and that's one of the reasons that we drove towards using high assay, low enriched uranium. Is to stay within that tier 2, to stay within tier 2, but also to make sure that we ensure the probability of our reactor causing an accident, stays well below the objective criteria of 1 in a million, as outlined in SPM 20. So in conclusion, I really want a foot stomp, right? I mean, for Draco, we absolutely are dedicated to producing revolutionary capability for the United States, but at the same time, it's absolutely our top priority to maintain the safety for the public while we launch this system, and to meet or exceed the guidelines that are laid out in NSPM 20. So if you go forward one more, I'll just show you a cool picture that you've already seen. And Ray, I'll pass it back to you.
All right. Yeah. Thanks so much, Nate. This is really cool stuff that you're doing with the Draco program. I'm kind of envious in a way, and I know a lot of questions are coming in, and we'll get to those a little bit later, but next we want to go to Dr. Anthony Calamino. He's going to talk about the programs going on in NASA in the future. And I don't know, Nate, they kind of match with Draco. I don't know which one's cooler yet, the ones that NASA are doing or Draco, but everyone can judge for themselves. So Anthony, do you want to take it from here?
Sure. So I'm going to talk a little bit more about mission sets than I am going to talk about some of the regulatory concerns. I think Nate and Tracy have covered that pretty well for us. So if we can move to slide 2. And basically, the space nuclear technology portfolio is relatively new to NASA. I mean, we've looked at fission technologies for quite a few decades. The SNAP-10A is an example of some of the technologies that we've looked at to generate power. More recently, we've been focused on both our lunar mission and our Mars mission, and we're looking at power requirements in those two areas and advancing some of the fission system technologies and system capabilities actually fit a nice need for NASA's mission. Within my area for the fission technology development, we were looking at designing, building, and demonstrating a space-rated fission power system. It's going to be one of the first capabilities that we want to have, primarily because it will support our lunar mission and a sustained human presence on the moon. And so we also gives us an ability to operate in craters, permanently shadowed craters, as well as a little bit more autonomy or independence from some of the long lunar nights. The other activity, which is quite closely aligned with Nate's and Draco, is the advanced deep space nuclear propulsion systems. These are the architectures or transportation methods that we would be using to conduct a human exploration mission of Mars. These systems are high risk technologies right now, and we're looking at both the nuclear thermal propulsion system that Nate talked to in detail, but we're also looking at the nuclear electric propulsion. We're using electric propulsion devices and using the nuclear reactor to develop electricity to power those. Currently, actually, that NEP system is the baseline system that NASA is looking at for its Mars architecture. So we're doing trades on both. I'll talk a little bit more about them and some of the investments in there. And then obviously looking to collaborate and develop working relationships with other government agencies such as Nate's and Tracy's, looking for synergistic technologies related to materials, fuels, and development and fabrication efforts. And as always, NASA wants to look to get industry engaged as well as academic interests. And we'll try to align as we can with some of their approaches and solutions. Next slide. So just a couple of things. The fission surface power, I talked a little bit about this. It does give us that solar independence, that continuous power production. And I'll talk a little bit about what our threshold power requirements are. They're very similar for the moon and for Mars. They are required to have a sustained presence for the long duration lunar operations. And we're looking at the moon is sort of giving us that foundational system to demonstrate that power capability and then work out some of the design modifications or some of the other extensibility options that we would have to move that capability to Mars. On the nuclear propulsion side, the big challenge for NASA right now is looking at these opposition class missions. Read opposition class missions as sort of coming in early during the synodic period with Mars, which is around 2 years, and having a short duration fast transit out to Mars, stay for a short period of time on the surface of Mars, 30 to 40 days, and then leave and still have an opportunity to return to Earth. These typically would be about 750, 700 kinds of day missions. That would reduce the amount of radiation exposure to the astronauts. It's the big advantage for us there. It's going to require extending some of the performance requirements for the NTP system. It also puts some challenging burdens on the NEP system. And of course, for both, we're looking at critical cryofluid management technologies for the propellants and some of those other systems. So a lot of these areas that we're investing in these technologies have direct synergy with DARPA. And we're working with Nate and his group to collaborate where it makes sense. Right now, the agency has prioritized the lunar surface power as the investment area and continues to support the propulsion capabilities as well. Next slide. So looking a little bit more in detail as far as what we're doing with the propulsion and power areas, talk a little bit about the numbers. The fission surface power system is actually managed out of NASA Glenn in Cleveland, Ohio. The propulsion activity and investments are managed out of NASA Marshall, which is in Alabama, Huntsville, Alabama. On the fission power system, we're looking at lightweight 10 kilowatt dynamic power conversion technology or system on this one. We are interested primarily in HALO solutions, although we're open to do comparisons and trades on HEU still, but HALO has a lot of advantages to us. And we are engaging or actively looking to engage design and trade space studies with industry on that power system. On the space nuclear propulsion, the reactor on that one is much larger. We're looking at about, for NTP, we're looking at a 500 megawatt thermal reactor to drive high ISP engine. These engines are going to be 900 second ISP, but I think for folks that work reactors and some of the materials technologies, what that really translates into is temperature for the reactor and for the propulsion component. And in this case, we're looking at a reactor that would be operating at about 2900 degrees Kelvin to produce a hydrogen propellant that would be at about 2700 to give us that ISP that we need. We are also working with NASA and DOE and DOD to establish a fuel production capability. This is a coated particle fuel production capability, and it has interest for DOD's PALE program. Obviously, the TRISO particle has had quite a bit of development and interest out of DOE over the recent decades. And NASA is looking at that as a fuel form that we can use, we believe, for a lot of the different applications. So there are studies that show that we can use it for the surface power system, for the lunar mission, for NTP. As a matter of fact, that's our primary fuel approach for NTP, as well as applications for NEP. And we currently are engaged in an industry solicitation. It's on the street. We close those out at the end of March. This will be a design effort, and I'll talk a little bit more about that. Next slide. So just a little bit about the fission surface power details there. The integrated story, we are working closely with DOE on this, looking at DOE's subject matter expertise, looking at DOE also to help with their authorities on nuclear regulation and their ability to solicit and get some of procurements and contract efforts with reactor development companies in industry. We are currently looking at a sort of a two-phase approach, one first being a design, second lead up to a build and demonstrate. We'll do a lot of development on the ground, and that will be an activity that hopefully will lead us into a site-qualified system for power for the moon that we can launch in the late 2027, perhaps. Right now, activities that we've had in the May push into 2028. And then we would demonstrate that capability on the surface of the moon for about a year and make sure that we understand the system, run it through its paces, and then look at what other modifications or changes we might need to do to make that same performance capability work on the surface of Mars. As I said, we're looking at HALU solutions that enables us to engage a broader sector of industry, as well as allows us to reach out and talk with some of the industry and academic interests to bring them in and help with some of the fuel development and moderator material development efforts. Next slide. Go through it quickly. We're looking for a 10-year lifetime. We want modularity. In other words, we do expect the power to grow. 10 kilowatts is getting in sort of threshold power requirement that we have, but we do see in-situ ISRU that we would need to do. We also need to look at other sustained robotic missions that would be on Mars. So right now, the thought is that we would be at 40 to 50, perhaps even 100 kilowatt power requirements on the surface of the moon that we would demonstrate. We do have a government reference design, which is a segmented moderated HALU system. We use that system to inform our investments on NASA's side and to invest in areas where we think we can get some early work done and reduce the technology development risks to industry. And that segmented reactor is again, a moderated reactor using fuel. And the request for information was put out in February. We are, and with the change in administration, there's been a little bit of a delay in that, but we would like to get that looking at right now. A little bit different of what NASA's doing, because we are stepping in this area, is really leaning on the experience of DOE, as well as some of the experience out in industry to define what does it mean to design a safe fission reactor, how that would be tested and verified for space applications. Obviously, we're going to work together on that. But using some of industry's design knowledge and design tools and bringing those into the activity that we're using to get that capability out there. And there's been quite a bit of strong interest from industry on this area to participate. And they're actually looking for commercial products that they could use either in LEO or also for some of the commercial activities that we would envision for the surface of the moon. Next slide. On the space nuclear propulsion side, next slide. A little bit of the story there. Nuclear thermal propulsion is our primary investment right now. That's actually where we do have this significant amount of investment in this area. We've been averaging in the $30 to $50 million a year on these investments for the propulsion side. As I said, we really see this big challenge here is getting the reactor temperatures up. That pushes materials knowledge, our understanding of material performance in these temperatures to their limits. So there's a lot of activity looking at how we would design those materials and how we're going to characterize those materials. I already talked about the common use of fuel production and the collaboration with DOE, but I kind of want to expand on that collaboration with DOE here. And I should have really talked about this more in the fission power activity as well, is that we have a blended team, and it's very much of a blended team between NASA and DOE. As a matter of fact, for the propulsion side, we've taken in one of DOE's folks from INL, and they are a subtop manager for our area in NASA, and so they basically are on full-time with one of our fuel development activities, which is really one of our key investment areas. So there's a lot of engagement, regular weekly meetings, a lot of across the fence kind of exchanges in terms of technology. And it's been working very well. I've been very happy to say that these teams are productive, and everybody has a piece that they're playing in terms of advancing that capability. The other area that we're looking in nuclear electric propulsion, we don't have a lot of investments in there. We do have some electric propulsion investments, some of the electronics investments on the PMAD side. It is currently the agency's reference configuration. It has a lot of advantages of fewer launches from Earth to get the capability in space. And it also has a little bit, it has a lower mass that we would use to leave Earth for that departure. So there are some economic and advantages to that capability. And it also has some longer range interest for NASA for some of its deeper space missions to the outer planets beyond Mars. Talking about the nuclear thermal propulsion on the next page, the reactor designs will use, as I said, the high assay, low enriched uranium. That's across the board for power and propulsion. Right now, we're marching toward a subscale engine build on this, about 12,500 pound force thrust engine. Our idea is that we would deliver that engine in the late 2020s, and it is a system on the ground or in space. That decision hasn't been made. That will close out. We released it on the 12th of February. It will close out at the end of April. This will be for phase 1 contracts. We're looking anywhere from 2 to 4 contracts, nominally 3. And really, this is just to get an idea of the preliminary reactor design. So it's really an engineering design activity to compare different concepts and approaches that industry would offer. We've actually had a couple years worth of trade studies that we've been doing with industry. So we have a pretty good understanding of what we're going to get out of that. As we move into the phase 2 contracts, we would actually start to look at building hardware and reactor hardware and conducting some tests, proof of concept on their design, making sure that we can get to the operating temperatures and performance conditions that NASA needs. And then eventually that would lead into a final contract where we would do a reactor build. And that would be the one that we would demonstrate. Next slide. All right, so on the closeout, I think here, just a couple more slides to do it. One of the other things that we have been doing in comparing NTP and NEP systems, I think NASA wants to make the right choice for this transportation system. It's going to be a significant investment for the agency. It would be looked at as having a long-term capability that we would use for our missions. We've engaged the NASA Engineering Safety Council to look at technology maturations of the two capabilities between NEP and NTP. There's been a lot of commonality in all of these studies. We've had an internal Mars transportation architecture study and then a National Academy of Science and Engineering and Medicine study, which just completed out, and they submitted their final report about a month ago. Most of these studies, and not going in through all these bullets, but they indicate that for a late 2039 human exploration of Mars, both systems could be available with a very aggressive investment posture, a little more aggressive with NEP perhaps than NTP, but they both could be made available. For that, one of the first things that we would want to do is probably demonstrate that capability in its full system in the mid-2030s on a cargo mission, and before we actually use it for a human mission. They both are interested in and would need to have CFM, cryo fluid management technologies. Liquid hydrogen is a significant challenge for zero boil-off. Obviously, we've launched that mass of that propellant into space. We want to keep it in the tank until we can use it in the engine. So we have a lot of investments that are going into zero boil-off for large hydrogen tanks in space. And on the National Academy of Sciences studies, they kind of indicated very similar things. One of the things they did point out is that for an NEP system, we are dealing with a lower TRL base, and we found that to be true in NESC and the Mars transportation study. But one of the challenges for NEP is scale up. You're going from some of the systems that we're used to some of the systems we'll need. We're talking about an 8 megawatt reactor in space. We're talking about using about 2 megawatts of electric power to run the system. These end up having large thermal radiators, significant amount of integration that would be required in space. So it's the scale up and complexity of integration that really end up being big challenges for NEP. And my last slide. So I'll just kind of get off the stage here. Power and propulsion, they're offering us a lot of opportunities. We do want to leverage industry design approaches for reliability and safety. We'll lean on both the industry and DOE for that. We want to make certain that we have a dominance of knowledge in the nuclear space technology capabilities. NASA is very much in line with supporting that. I think Nate talked to this about ground testing approaches. Full system tests on the ground are going to be difficult, particularly for NEP. So we're looking for innovative ways to test these systems before we put them into space. And as I said, some of the challenges we're working right now are commercial alignment, basically making certain that the government is investing in the right areas for risk reduction. Obviously, always with the government is to maintain stable funding profiles. And then one of the activities that will continue to evolve is really what do we mean when we say generating for system? Efficient system in terms of operational reliability for use either as a transportation system for Mars or as a power system for human operations on the surface of another planet. So, and that's the end of my talk.
All right. Well, thank you, Anthony. All of you did a great job, I think, with this is some exciting programs going on. I wish this session was about an hour longer because we just got a whole bunch of great questions that come in. So I'm going to get started on those with the time we have left. And this one's kind of for all of you. I think, Nate, you kind of started to get at this when you talked about launch safety in propulsion systems like a Draco, and we talked about the review panels, the INSERB, and we look at launch safety, and so what do you think from a launch safety standpoint, or fission systems at the launch stage more difficult from a safety standpoint, or is it maybe the radioisotope power systems with heavy loads of radioisotopes? So I think, Nate, why don't you start, since you kind of started to talk about that during your talk?
Sure. Yeah, absolutely, Ray. And to some degree, I mean, what I was trying to get at with my part of the presentation, right, was that to some degree, it's not necessarily like one is more difficult than another, but what certainly is true, though, is that we have a long history that helps us to make ourselves comfortable with launching RTGs with radioisotope power sources, right? We have a long history with that, and we can kind of look back at previous programs and say, well, this is what we did then. It was safe then. We've shown and proven through the best methodology we have, right, which is experience. But then when you get into actually launching reactors, it's very different, right? And what we've found, even kind of within the launch community, is explaining this is a nuclear reactor, right? And then just being able to explain the difference to kind of our launch community as well, who's not necessarily made up from folks from the nuclear community, right? But marrying those two things up, and there's a little bit of an education that needs to happen, right, on nuclear reactors and how they're different, right, and how when we launch them, they're essentially cold metal, right, with similar hazards to like a heavy metal like a lead versus like a radioisotope, right? And so probably if I had to stand up in front today and say which one's more difficult, a lot of it is, the difficulty we have with reactors, a lot of it is just a different mindset that we have to get into for reactors, and kind of the education process to go from kind of a radioisotope centric mindset over to a reactor. I think both are absolutely doable. Obviously for radioisotope power sources, but for a reactor, I think we're absolutely, this is a doable project. But that education part is certainly a hurdle that we need to clear over the coming years.
Yeah, thanks, Nate. And maybe for Anthony or Tracy, as we look at programs that are responsible for doing the safety analysis for space launches, on fission systems, how do you take into account, possible reentry? Let's say you've launched it. Yeah, maybe there is no fission product inventory to the reactor at launch because it hasn't operated yet. But then the thing gets into space, you operate it, and then it can possibly have fission products build up in space, and then somehow there's an event and you cause reentry. Do you account for those types of things as you look at the hazards for these future launches?
Hi, Ray. It's Tracy. I'll take that on. Yes, absolutely. And I think one of the great things with NSPM 20 is that it's going to allow us to really leverage, at least from the department's perspective, how we identify those hazards or potential accident scenarios up front early in the process. One thing I failed to mention, one of the things that we're trying to be transformative with NASA is start to developing safety analyses that are based on the technology independent of the mission, so that the missions walking into looking at how they're going to power, what power needs do I have, will have all that information up front rather than, developing that information 2, 3, 4 years into their planning and design efforts. So it's going to really kind of move that safety discussion a lot further into the process up front, very clear. And, if we look at, when we have those thresholds that are identified in NSPM 20, it's going to allow us to identify what are those high risk hazards. And in prior launches, we've looked at everything from initial ground phase all the way up to complete to launch and potential reentry. So all of that does get captured in the process. So, those are things we want to continue to work on and move forward with.
Thanks, Tracy. The next question I'm going to direct to Anthony, and then maybe Nate can jump in. I mean, both of you in your discussion talked about the propulsion systems and using high assay LEU, and to define it, the high assay LEU is uranium enriched to less than 20%. And rather than, let's say, a weapons grade, very, very high proportion of U-235. And you guys brought up a high assay LEU, and where are you going to get it? And you mentioned the advantages of it. I think, Nate, you did with regard to NSPM thresholds, and maybe you can explain what that threshold is. But Anthony, do you want to start with high assay LEU and why you chose that and where you're going to get it? All right. It looks like we maybe lost Anthony. He's been having some trouble with connections here. So, Nate, that means you have to take the question on.
Sure. Well, I'll take on the question from a DARPA perspective, certainly. So that's a really great question, right? I mean, when we look at DoD applications, right, usually performance comes first, right? And from our perspective, when we look at when we looked at high assay low enriched uranium versus highly enriched uranium, it really came down to looking at NSPM 20 and this tiered system, right? So for anyone that reads through NSPM 20, right, you see that tier 2 accounts for, in terms of reactors that both fall under two categories, right? One is using low enriched uranium, and two is being able to prove that you have that one less than 1 in a million chance of, I think it was a 5 rem dose to the public, right? And so it was both risk-based and enrichment level based. And what that tier 2 allows within NSPM 20 is that the approval authority is delegated from the presidential slash Office of Scientific Science, Technology, and Policy level down to the agency director, which in our case would be the Secretary of Defense. And that's a huge change for us, especially, and an enabler. And then for tier 3, right? If you want to go to a highly enriched uranium system, that would drive you to a tier 3 system just automatically, regardless of the risk of dose to the public. And so that really is what. Go ahead, Ray.
Yeah, thanks, Nate. And sorry, Anthony, you didn't get a chance to answer the
I've been having a lot of challenges with my system. Yeah. Thank goodness it didn't kick me out. Hopefully while I was talking.
Well, I really have to apologize. We've ran out of time. The session has
no problem
quickly, and we had a lot of great questions. Like I said, I wish we could have stayed on another hour and had this conversation because it's really great stuff. I just want to thank all of you on the panel. Tina, thanks for backing me up as a coordinator of this, and I really appreciate all the participants with the great questions we had come in. So with that, thanks again, and we'll close the session. And have a great day. Thank you. Yep, thank you.
Thanks, Ray.
Yep.
Bye.
Thank you.
Bye.